Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with gas mixtures, and we will be discussing Dalton's law of partial pressure, Gay-Lussac's law of combining gas volumes, Avogadro's hypotheses, and molar volumes of gases. I'm going to ask you to read some points that are made here about the applications of gases and gas mixtures. So it speaks about airbags that depend on a certain volume of nitrogen gas to be produced in less than 40 milliseconds after a collision. To refloat sunken objects in bodies of water. Working of the steam engine. Diagnosis of metabolic and respiratory disorders in scuba diving. Now we look at how Dalton formulated his law of partial pressure for each non-reactant gas in a mixture. English scientist John Dalton hypothesized that if in a mixture of gases there is no reaction between them, and that if each gas behaves independently of each other, then each gas will contribute its own partial pressure to the total pressure of the gas mixture. He carried out a series of experiments to test his hypothesis. In these experiments, he placed a fixed number of moles of a gas into a cylinder of known volume, and he recorded its pressure. He repeated this for different non-reactant gases. Finally, he placed all the gases into one cylinder and measured the new total pressure of the gas mixture. So the results of these are illustrated in the figures below. So let's look at these figures here and see what is happening. So in the first cylinder, but first of all, note that each of these four cylinders here has the same volume. Okay, so in this one, he placed 5 moles of nitrogen gas, and he measured the pressure unit to be 5. Okay, in this one, 3 moles of helium atoms. Okay, that's a gas too, and the recorded pressure was 3 pressure units. And in this one, he placed 4 moles of oxygen that gave a pressure of 4 units. Finally, he dumped all of these into one cylinder and got a pressure of 12 units. There appears to be a relationship between the number of moles of gaseous particles and pressure. Here you're having 5 moles of molecules, and we're getting a pressure unit of 5. In this one, you have 3 moles of helium. Doesn't matter, it's a gaseous particle. In this case, it's atoms. We get a unit of 3. And in this case, 4 moles of oxygen gave a pressure unit of 4. And then look, when you clump all of these together, you're having 12 moles of particles that are giving you 12 pressure units. So there appears to be a relationship between the pressure and the number of moles of particles that a gas has. So this table here now encapsulates for us the relationship between the number of moles of particles and the pressure unit. So again, there's a repeat of that. In figure 1, you had 5 moles of nitrogen gas, you get 5 pressure units. In second one, 3 moles of helium atoms, you get 3 pressure units. Oxygen 4, and the total number of particles here is 12 moles, and you get 12 pressure units. Okay? All right, let's see how Dalton used the analysis here to make his law of partial pressure for each non-reacting gas in a mixture. So, Dalton formulated his law of partial pressure, which states that the total pressure of a mixture of non-reacting gases is the sum of the partial pressures of the individual gases. And there you can see exactly that's what we said. The total pressure here of the whole mixture here is the sum of the partial pressures of each of these non-reacting gases. Why non-reacting? Because when gases react, they will form fewer number of molecules. You want these to stay by themselves to see the relationship between particles and pressure. What is saying here? Regardless of what type of non-reacting gas is placed in the container, whether it be in form of molecules or atoms, each particle will have the same pressure unit. Okay? So let's look at the expression of partial pressure now. The total pressure is 12 pressure units. So the partial pressure of nitrogen will be 5/12 of the total. Helium will be 3/12, and oxygen will be 4/12, and all together will constitute the entire pressure, which is 12/12. Okay? So the partial pressure P1 of that gas plus the partial pressure P2 of that gas gives you the total pressure of the gas mixture. So here's a problem here. You have a 2-liter flask containing these 3 non-reacting gases, and these are the respective partial pressures. What is the total pressure? Just add them all up, and that's what it is. Next question, maybe you can watch this one again. A gas cylinder has a mixture of oxygen and helium. If the total pressure is 10 atmospheres, but the partial pressure of helium is 9, what is the partial pressure of oxygen? Of course, oxygen and helium make up 10, that is 9, oxygen must be 1. How might the partial pressures of inhaled oxygen, carbon dioxide, and water differ from those exhaled? You need to know a little bit of biology here before you can answer this question. When you inhale gases, you're inhaling some carbon dioxide, oxygen, and nitrogen. Well, nitrogen doesn't get affected because whatever nitrogen you breathe in comes out back, right? But when you breathe in oxygen, what happens? Some of it leaves the lungs and enters the blood. So the partial pressure of inhaled oxygen will be higher than that of exhaled oxygen. Carbon dioxide, of course, you know that is a respiratory product. When you breathe in, it has less, so when you breathe out, it's going to have more from cellular respiration. And of course, you know, if you blow your breath close to a mirror, it fogs up. That's because more water is coming out from your breath than what you're inhaling. So the partial pressure of exhaled water is going to be more than that of inhaled water. Okay, now we're going to talk a little bit about vapor pressure. Okay, vapor pressure of water. Okay, this diagram here will explain to you what is meant by vapor pressure water and why that is important when we are collecting gas over water, and we want to know what is the volume of the gas collected and the pressure of the gas collected too. Okay, watch this now. Show you how a gas is collected over water. Let's say inside here a reaction is taking place that is producing a gas. You can have lots of reaction there. You can have hydrochloric acid reacting with, say, magnesium. You can have some calcium carbonate reacting with hydrochloric acid. You have a tube here, there's a stopper there. The gas is going to come out of that glass tube in there. You can connect that to this rubber tube in here, okay? So when you connect that to the rubber tube in here, whatever gas is produced goes into the rubber tube in here. Okay. If you want to measure the volume of gas produced, you have to get a graduated measuring cylinder. You fill the cylinder with water and invert it into a pneumatic trough that is partially filled with water. So this is called a pneumatic trough, and it's filled with water there. And you put that measuring cylinder on a stand that has a hole. So this tubing here comes through that hole, and any gas that is produced will rise and it will depress the water downwards. So the gas that is collected will be up here. that's where the gas will be inside here. Inevitably, because this is water here, some water molecules will vaporize and enter here and mix with that gas. So the pressure inside here would not only be as a result of the gas accumulated there, but part of it will be due to the water molecules that have evaporated from the liquid here. And the pressure that's contributed by the water there is called the vapor pressure of water. This table here shows you the vapor pressure of water at different temperatures. Why is it at 25 it is 3.17, and let's say at any other higher temperature, say 40 degrees Celsius, it is 7.3. Why does the vapor pressure of water gets higher as the temperature rises? Anybody? As the temperature rises, the water molecules here will gain more kinetic energy, okay? And therefore more of the water molecules will vaporize to mix with the gas, and as a result of that, they'll create more pressure inside here. That's why now you have to know what temperature you're doing this experiment with. So supposing now you are doing this experiment at 25 degrees Celsius, and the pressure of the gas collected, total pressure of the gas collected, was recorded to be 90 kilopascal, right? At 25 degrees Celsius. This is the total pressure of the gas as well as water vapor. So you have to go and see what is the vapor pressure of water at 25 degrees Celsius, and you minus that from this here. So you minus this value here from the total pressure, and that will give you the real pressure of the dry gas. So let's go down and talk a little bit more. I want to make another point here. It's a little bit of physics, not bad. I asked you a question when we did atmospheric pressure, and the question was, if Evangelista Torricelli used water instead of mercury to see what column of water the atmosphere would be able to support in a tube, what will be the difference in height? Okay, before we go over difference, let's look at this one here. Okay, so here we found that the height of the mercury was 760 millimeters. For you to have seen that, you had to take a glass tubing that was having a length greater than 760 milliliters, because the mercury height will be at least 760 milliliters. Look at this. Mercury is approximately 13.5 feet denser than water. So the atmosphere will be able to support a column of water all these times more than this, which will be equal to all of that. So if we have a cylinder and we fill it with water, the water will not go down unless it is higher than that, right? So if a cylinder is filled with water and then inverted into a water-filled pneumatic trough, it will remain full. Let's go back to this diagram here. If that was filled with water and no gas went inside, it will remain full because the atmosphere is pushing that up and is capable of pushing it up to a higher degree, okay? So just that point I want to make. Now, next point. Let us suppose that this cylinder here was used to collect a gas. As the gas was collected here, it was creating a pressure that was acting against atmospheric pressure. The atmosphere is pressing on this liquid in this pneumatic trough, and it is pushing the water here, and it was capable of pushing that water all that height. So when the gas is being collected, it is pushing down against atmospheric pressure, but just wants to keep that thing here. The point to be made is this. When the gas has lowered the water until the level inside the measuring cylinder is same as the level as the pneumatic trough outside, then the gas pressure is equal to atmospheric pressure. That's the only time when the pressure of the gas inside here is equal to atmospheric pressure, when the level of the water in that measuring cylinder is equal to the level of the water in the pneumatic trough. So I hope that was helpful there. So you put things in some perspective there, okay? All right. So let's look at this problem here. The gas is collected, the pressure of the gas is 100 kilopascals, where the temperature is, when it was collected, was 25 degrees. What is the pressure of the dry oxygen? It definitely can be this, because this is water plus oxygen. So look at the vapor pressure of water at that temperature. It's 3.17. Subtract that from the total pressure, and that was the pressure of the dry oxygen. Now we go on to Gay-Lussac's law of combining gas volumes. That's his whole name there, Joseph Louis Gay-Lussac. Gay-Lussac observed that when gases at the same temperature and pressure react and their volumes are absorbed, they do so in ratios of small whole numbers. So let us see some examples here. Here you're having in these cylinders here, you have carbon monoxide here, CO, CO. You can see that this one here, guys, can take up another oxygen here to form carbon dioxide. So we're giving it oxygen to react, okay? Molecular oxygen with molecules of carbon monoxide, and they give you carbon dioxide here. So look what is happening. You have one volume here, another volume of carbon monoxide, and one volume of oxygen gives you 2 volumes of carbon dioxide. Okay, you can see difference in the molecules there. All right. So if we put all of that together, we can say 2 volumes of carbon monoxide require 1 volume of oxygen to give you 2 volumes of carbon dioxide. Okay, so that's what he's saying. When they react, they do so in these ratios here, okay? Whole number ratios. All right, some other examples here. Got the volumes, all right? 1 volume of hydrogen reacting 1 volume of chlorine to give you 2 volumes of, all right, hydrogen chloride. Nitrogen is reacting with hydrogen to form ammonia. You need 1 volume of nitrogen with 3 volumes of hydrogen, and you get 2 volumes of ammonia gas. Based on these observations, Gay-Lussac formulated his law of combining volumes, which states that, again, in any chemical reaction involving gases measured at same temperature and pressure, the volume of the gaseous reactants and the gaseous products are always in simple ratios of whole numbers. All right, now watch this now. Got some controversies here as developed. After Gay-Lussac formulated his law, it was challenged by John Dalton, who believed that gases were made up of single atoms according to his atomic theory. John Dalton did not realize that gases such as hydrogen and chlorine and oxygen and so on exist as diatomic molecules. As such, he said it will be impossible for 1 volume of hydrogen reacting with 1 volume of chlorine to produce 2 volumes of hydrogen chloride. So the following figure depicts his contention. This is his contention. He's saying, look, according to my belief, chlorine is an atom, this is an atom. If they come together, see, look, you can't get 2 volumes because these combine together to form hydrogen chloride. Only 1 volume you should get. But this is what he believed, but this is not necessarily correct, okay? See who comes to the table now. While these 2 guys were still at loggerheads, they were still in total disagreement, Italian physicist Amido Avogadro, remember a friend, proposed a solution to this dilemma. These are his hypotheses. He says that equal volumes of gases measured at the same temperature and pressure contain equal number of particles. So hold that there. Equal volumes of gases measure same temperature and pressure contain equal number of molecules. So if you have, look, 10 different gases at the same temperature and pressure, and you have the same volume, and you count the number of particles inside, they'll have the same number of particles inside. This other hypothesis is of special significance, since it will bring about reconciliation between the differences in viewpoints of Dalton and Gay-Lussac. He said these molecules, such as oxygen, chlorine, and hydrogen and nitrogen and so, are divisible into half molecules. Okay, call them half molecules. That is, each of these molecules must be composed of two atoms that splits up into individual atoms before they react. Okay? So he's saying, look, this chlorine here, this chlorine molecule, it has two atoms, and this hydrogen molecule has two atoms. Before they react, they will split up. They must split up like that. Okay? So you get in two atoms. Okay? And of course, this one will combine with that one there to give you that one there, and this one here combine with this one to give you that one. So he came to the rescue. Okay? Avogadro. So this is what he says now. Look, these molecules here are diatomic molecules, right? One of these here will react with one of these. So in fact, you are going to get two volumes there. And the same thing we've seen at the top here, right? These here explain what is happening here. All right, so this is the solution to that dilemma there. Avogadro says, look, these molecules are diatomic molecules, okay? And when they react, they break into two atoms. And that's why you end up with that number of volumes instead of one, as proposed by John Dalton. Okay, now we do molar volumes. But before we go to molar volumes, I want to recall these, something we did talk about density and volume. Okay, good. Density is equal to the mass of a substance divided by its volume. The volume, therefore, will be equal to, if you take volume across there and bring down density, volume of anything will be equal to the mass of it divided by its density. So hold these two together now, especially this one here, as we talk about molar volumes of gases. We go back to Avogadro's first hypothesis. What did Avogadro say? Equal volumes of gases measured at the same temperature and pressure contain equal number of molecules. So if you flip this around now, based on his first hypothesis, it can be deduced that equal number of gas particles measured at the same temperature and pressure must occupy the same volume. So we just reversing this thing. Equal volumes contain equal particles, right? Number of molecules of particles. Therefore, equal number of particles at the same temperature and pressure must be having equal volumes if you have different gases. Okay, so okay. This means that 1 mole of any gas, that number of particles at 0 degrees Celsius and 101.3 Kelvin, this is standard temperature and pressure, should occupy the same volume. All right? 1 mole or that number of particles, equal particles, okay, of different gases, any gas at the same temperature and pressure must have the same volume. Let's look at this table here. These are gases. You can find out the density of a gas from a table of data. That's the density there for each one of these here. The molar mass is also found. These are the molar masses within mole concept. We show you how to find molar masses of things. We said density is equal to mass divided by volume. Therefore, the volume now will be equal to mass divided by density. So here we have the molar mass, and this is the density. If you divide molar mass of each of these gases by their specific densities, you will get the volume. In this case, if you look here, you can see sparing little differences. We can round all of these up to 22.4 liters. So at 0 degrees Celsius and 101.3 kilopascal, which is STP conditions, the molar volume of a gas is 22.4 liters. Okay? Each one of them will have Avogadro's number of particles. All of these will be molecules except neon, which will be atoms. Okay? So now we have established one point. At STP, the molar volume of any gas is 22.4 liters. But we said the more convenient set of conditions are at SATP. This thing can be done experimentally. If I have 3 cylinders here, right? And these plungers are right down at the bottom. There's no gas. And in each of these, we allow 1 mole of gas to be inserted, 1 mole of hydrogen, 1 mole of nitrogen, and 1 mole of argon. Okay? This plunger will go up and it will be exactly the same in each case as long as the temperature and pressure of these gases are the same. And it works out to be 22.4 liters, and of course 1 mole of anything will have Avogadro's number of entities, in this case is molecules, and because that's an inert gas, it's in the form of atoms. Okay? But we said this is the more convenient way, okay, of representing things. If the volumes of the gases were measured at 25 degrees Celsius and 100 kilopascals, volume will be 24.8 liters. Why? Because look, at a higher temperature compare this to 0, the increase due to the temperature there will overwhelm the decrease caused by a little fall in pressure. So I hope that was useful. I see you